So today we're going to be covering the column questions 41 through 56. So let's go ahead and get started with the first one. We have question 42. Okay, so what we're looking at in question 42 is we're looking at transformations and how to describe them. We see the fact that we have the function f of x. So f of x is equal to the log base 6 of x, and we want to describe how did it get from this function to this function. So what's going on from here to here? And we have a 3 log base 6 of x plus 4. Now, one of the most common things that you're going to ask yourself is the plus 4 going to be part of that x? And now, unless otherwise specified, we're going to assume that it is not. We don't see a set of parentheses here, so we assume the set of parentheses is around typically what we call the immediate base, but in this case it's around the immediate log. So the plus 4, because it wasn't included in a set of parentheses, we assume that it is outside. So we see that there are a couple transformations that have occurred. We notice that we've gone from a regular log to a log times 3, and that times 3 means it has been stretched. And it's been stretched 3 times. Now, if that number was between 0 and 1, albeit the effect would be the same, it wouldn't be called a stretch, it'd be called a compression. But we've got a stretch times 3. The second thing we notice is that 4 that we were talking about. Because the 4 is on the outside and not included in the parentheses, that is an up and down shift. So this has been a shift up by 4 units. Boom. And there we go. So that is the end of question 42. Let's take a look at question 43. Okay. So now 43 is a very similar style question. We're given a parent function log base 6 of x, and we now have to describe the transformations negative log base 6 of x minus 1, and we see that that minus 1 is included in a set of parentheses. So let's go ahead. If we take f of x is log base 6 of x, what happens to get this equation into this equation, which is a negative log base 6 of x minus 1. Okay. So we're going to go through the same set of analyses. I noticed that it went from a positive to a negative. This means it has either been flipped or what we would call a vertical reflection. The graph has been flipped vertically. So what was pointing up is now pointing down. What was down is now pointing up. The second thing that we notice is that inside those parentheses, let's do this in a different color not to confuse with the last one, is that I have a minus 1. Now that minus 1 means the graph has been shifted to the right by 1 unit. Awesome. So that brings us to the end of question 43. Let's take a look at question 44. Okay. So at question 44, we are going to be finding the inverse function of f of x is equal to 5x. So let's take a look at that. So because we have this function written in f(x) notation, we may notice that we're looking at y equals 5 to the power of x. And to rewrite a function in the inverse, we swap the x and the y. So instead of writing y equals 5 to the power of x, I'm going to write x equals 5 to the power of y. And I'm going to resolve for the y value in this new equation. So these two are inverses of each other. And in order to isolate the y, I'm going to have to rewrite this in logarithmic form. Now, logarithmic form, my favorite part of this, is we get to drop the base. So if this is a base of 5, this is going to be log base of 5, and we just swap the other two variables. So log base 5 of x is equal to y. And boom, we have ourselves our inverse function. Now, this is written in the equation format. If we want to write it in function notation, all we do is we say, hey, f of x is equal to log base 5 of x. Awesome, so we have our inverse function in function notation. The other way, as we've done it prior, is to simply just solve for x, in which case what we do is we would rewrite it as drop the base, so this would be log base 5 of y is equal to x. and this is the inverse orientation of that function. This is the inverse function itself. Awesome. So now that we've seen that one, let's take a quick look at 45. So 45 says find the inverse function of log base 4 of x. So we're looking at it from the other perspective. If f of x is log base 4 of x, okay, let's take a quick look at how I would rewrite that. First off, instead of f of x, I'm going to write this as y equals log base 4 of x. Now, I can go through with our previous example and just solve for the other variable and then rewrite it in its new form. Or if you like swapping the variables initially and then resolving for that, you'll get to the same value no matter which way you do it. So I'm going to go ahead and I'm going to rewrite this in exponential form, which means that I drop the base. If I have log base 4, that is the base of my power. So 4 raised to the power of y is equal to x. So now this function is rewritten. This is the same orientation, the same function, written in exponential form. If I want to write it in the inverse function notation, I would simply write, okay, actually, before we even get into that, I would write it as 4 to the power of x is equal to y. And now this is the process. As of right now, this is one equation. This is where we jump over to the inverse. Now this is what we would rewrite as our f of x is equal to 4 to the power of x. Boom. Again, same equation written in a different notation. This is the inverse of that original function. Perfect. So that's the end of 45. Let's take a look at 46. Okay. So 46, what is the base of log 8, 3? Okay, so I'm looking at this expression, log 8, 3. So this is asking if we know how to rewrite logarithmic functions. The first thing that I notice is that anytime I have a power in a log, I can rewrite that as 3 times the log of 8. What that doesn't tell me is what is the base of log. Well, don't forget, we always assume that if I cannot see the base of log, then it is an assumed base 10. This is what we call the common log. The idea is that a base 10 is considered common, so we don't actually write it. It's the same thing as writing something like x to the first power. We don't ever actually write the first power. We just assume that's the general exponent. If we don't write the base on the log, we assume that is the common log. We never show it. So this has a base of 10. Perfect. So that's 46. Let's take a quick look at 47. Okay. So we're asking the same question, but instead of that notation, we have this ln. So I want to know the base of the natural log of x to the 4th power. Well, again, the first thing that we can do is we can rewrite this by taking that power and rewriting it as a coefficient. So 4 times the natural log of x. Now, you might be tempted like the previous one. Well, I don't see a base, so I assume this might be the common log. But if you remember, the ln is considered the logarithm naturel, or the natural log. And a natural log has an assumed base of, so this is a natural log. And what a natural log does is it has a base of 4 times log base e of x. So if I have a log base e, we generally write that as an ln for the log naturel because it was originally written in French. So this has a base of e, of Euler's number. Bonus points if you know what that e is. That e is a never-ending decimal similar to pi, if anybody wants to check out what that might be. Okay. So that's the end of 47. Let's pop over here and start out number 48. Okay. Number 48, we're looking at what is the base of log 3, 4 equals a. So we have this expression, log 3, 4 equals a. Okay. Well, no matter which way we write this, if we write this in logarithmic form or in exponential form, remember the expression, rewriting this, we always drop the base and swap. So if I drop the base and swap, we recognize the base of the exponent, or the base of the power, is going to be 3 in the same way that the base of this logarithm is also going to be 3. So I have a base of 3 no matter how I look at it. Okay. It's the end of 48. Let's take a look at 49. Okay. So 49 says, rewrite log base b of a equals x in exponential form. So we've actually already done a few of these in these last few examples. We want to rewrite this in exponential form. So we drop the base and swap. Log base b of a equals x. I'm going to drop the base of b and swap these two. That is the logarithm written in exponential form. So what you'll notice is several of these questions are just basic knowledge on how to rewrite logarithms. So see, that was 49. Let's take a look at question 50. We're going to write log base 4 of 1/256 equals -4 in exponential form. So log base 4 of, I'm going to rewrite this with a parenthesis. Sometimes my handwriting is not the best. Okay. So I'm going to rewrite log base 4 of 1/256 equals -4 in exponential form. So I'm going to drop the base and swap. So 4 to the -4 equals 1/256. That actually makes sense, because if I were to rewrite this, I know that 4 to the -4 can be rewritten as 1/4 to the 4th is 1/256, which this looks a lot more familiar. The negative exponent just means it's a positive exponent in the bottom, hence the large fraction. But that's the end of question 50. Let's take a quick look at 51. Okay. So what we're looking at with 51 is, what is the approximate value of log base 3 of 7 to the nearest thousandth? Okay. So let's see, we're looking at log base 3 of 7, and we want to estimate the value of that. What this is testing is, do we know how to use the change of base? Depending on the calculator that you have, you may already be able to solve this. So if I'm looking at log base 3 of 7 and I have a TI-84, what I can do is I can, let's see if we can't show this whole thing, is I can plug in this expression directly into my calculator. I can go to either the log, which is going to be the common log. This is not the common log. So I'm going to go to the math functions and go all the way down until I see, oh, there it was, log base. Now, log base, when I hit that, it shows me, hey, what base would you like to put your log? Log base 3 of 7. Boom, it gives me my decimal equivalent. And we know we're rounding this to the nearest thousandth, which means this is roughly equal to 1.771. Now, let's say we don't have a calculator that does that. Let's say we have something that's like the TI-30. Well, the TI-36X Pro also does that same thing. If you look at where the log button is, I can either do natural log, regular log, or log base. Now, the way that I would plug it into here is I would say, okay, log base 3 of second, comma, 7, close my parenthesis. Oh, maybe I did that backwards. Log base 7, comma of 3. There we go. Yeah, so I did that backwards. Let's clear that and show you that. Log base 7, and what is the base of this log? 3. I get 1.77 right there. So I don't need to do anything crazy. However, if I am using this calculator right here, my log button is not nearly as fancy. And if I go to type log, it immediately says error. Okay, well, how about 3 of 7? Well, I can do the log of 3, or I can do the log of 7, but I can't do log base 3 of 7. So I have to use the change of base formula. And the change of base formula The reason why we rewrite this in exponential form using this phrase is the change of base is the same. Drop the base. So I'm going to create a fraction, dropping the base, log of 3, log of 7. And now with this, I can figure out what's going on. So I can say, this is a common log, which does have the capability right here. So log of 7, boom, is going to be this thing. So I have 0.845098004. We're assuming that we don't have a storage function. This one does, but we're going to go ahead and just assume that it doesn't, which means I'm going to write out all those decimal places. Do the same thing with 3. Log, and I have 0.477121255. Let's see what the equivalent of that is. So 0.845098004 divided by 0.477121255. And I get that same expression. So I get 1.771. So either way, we're really testing, no matter which calculator do you have, do you know how to use the change of base? Awesome. So now that we're done with number 51, let's take a look at number 52. Okay, so 52 is another one where we're approximating log. So I'm looking at what is the log base 2 of 12 to the nearest thousandth. So again, if I have a calculator like the TI-84 or the TI-36X Pro, all I do is I say, okay, I'd like to plug in, going to the math function, I'm going to go up so I can go to the bottom, base, and it sets up the equation for me. Log base 2 of 12, I don't need to do anything further. I get 3.58. Now that 4 is going to round up to a 5. If I don't have one of these, and I have the TI-36X Pro, I do the same thing. I just keep hitting the log button until I see log base. And we said, okay, log base is going to show log base 12, comma 2, and I get that same value. Or if I have this calculator, what we're going to do is we're going to have to use the change of base formula, which means I drop the base. So I have log of 12 over the dropped base of 2. And let's see what the equivalent of those two decimals are. So the log of 12 is 1.079181246. The log of 2 is going to be 0.301029996. And so what you'll notice also, if you're unfamiliar with how to type this in, I always type the number first, so 2, and then we hit log. And it shows me what the log of 2 is. Let's figure out what this abbreviated is going to be. So 1.079181246 divided by 0.301029996. And we get that same decimal, 3.58, and that 4 rounds up to a 5. One of the things you will want to avoid if you're writing out the decimals like this is you want to avoid rounding. If it says nearest thousandth, you may or may not be able to get away with just writing it out to the nearest thousandth. Let's check it out and see if that would work. So if I had 1.079, the nearest thousandths, divided by 0.301, I will get 3.585. But we see that 9 is now a 7. That's really close, because if that 9 wasn't a 7, let's say that 9 was a 6, now I'm looking at a 4, that's going to result in my answer going up or down by a decimal place, which may or may not cause you to lose the point on that individual question. So you want to write out as much as you can when you can. Let's take a quick look at number 53. Okay, so number 53, we're looking at 2 to the power of x is equal to 10. What is the value of x to the nearest thousandth? So we're doing the same thing we just did, but instead of jumping straight into the logarithm like we did right here, I got to figure out what would this be. So 2 to what power is equal to 10? Well, we could do this via brute force and just plug in random powers of 2 and say, okay, let's try, how about, let's clear this, 2 to the power of 1. It's not enough. How about 2 to the power of 2? 2 to the power of 3? 2 to the power of 4? Okay, so it's somewhere between 3 and 4. How about 2 to the power of 3.5? And this could take a very long time. But if I rewrite this in exponential form, I'm going to drop the base. Log base of 2 of 10 is equal to x. And we see that with this is the same question as what we just did up there. I could either plug in log base 2 of 10 into my calculator or do the change of base formula. No matter which one I do, let's see, I drop the base. In this one, I don't even need to plug into the calculator. The common log of 10 is log base 10 of 10. That is going to give me a 1 over what is log base 10 of 2. Okay. Actually, I am going to use this calculator with the change of base format. So I'm looking at the log of 2 is going to give me 0.301029997. Actually, we just did that right here, didn't we? It looks like this calculator has an extra decimal place. Regardless, if I take 1 and divide it by that number, I will get 3.32, we said nearest thousandth, 2. If I wanted to plug it in right here, I could do my math. Log base, let's see, log base 2 of 10 is going to give me that same evaluation right there. So no matter how you work it, 3.322 is our answer. Okay, so that's the end of 53. Let's take a quick look at 54. Okay, so if I look at 54, I'm going to write the expression that's equivalent to this. So I have 3 log x minus 7 log y. Okay. So what we want to do right here is I want to know how to rewrite a logarithmic form. The first thing that I want to do before I do anything to these logarithms is I need to get rid of the coefficients. Before I can combine them, I cannot have coefficients, which means I'm going to rewrite each of these logarithms with that coefficient as a power of the argument instead. So I'm going to rewrite this as log of x to the third power. And so think of that as log of x to the third power. It's not the whole expression cubed. It's just that x that is now cubed. And I'm going to subtract log of y to the 7th power. I'm going to do the same thing over here. I'm raising the y to the 7th power, not the entire expression. And now remember, these are both common logs, so assume there is a base 10. And because these both have the same base, I am allowed to combine the two different logs into one. Subtraction is going to mean that is going to be division. So this is going to be log of x cubed divided by y to the 7th. What I can do is I can take my two expressions. My initial function is going to be the numerator. Subtract, that will end up being the denominator. And again, because it's a common log, we know that's equivalent to a 10. So depending on how the question asks, you might have a 10 in there, you might not. Know that either way, that is a single logarithmic expression, which is represented by that up there. It's the end of 54. Let's take a look at 55. Okay, so 55 looks like we're doing more of the same. We're going to write an expression that's equivalent to, instead of subtracting this time, we are adding. So we have 4 log of A plus log of B. Okay, so we know that the first thing I need to do is I need to get rid of any pesky coefficients, and I'm going to rewrite them as a power. So I have the log of A to the 4th power plus log of B. Now I'd like to write these as one logarithm expression, and I can only do that if they have the same base. I know that both of these have an assumed base of 10 because these are both common logs. I know that with addition, it's not going to be a division symbol right here. Addition means I'm going to be multiplying the two terms. So this means I'm going to take a log of A to the 4th times B. And that's going to be all we need to do. If we have the common log in there, know that that will be there. Otherwise, we should be good. Perfect. That's the end of 55. Let's take a quick look at the last one in this column, 56. Okay. 56 says, what is the value of these two logarithmic expressions? So with this, let's go ahead and write this down. Log of 20 plus log of 50. Okay. So with this one, what we're trying to figure out is, how do I value these two things? Now, this may be on a calculator portion, in which case we can very easily, and we'll see what's going to be going on here, plug this in. So these are both common logs, so no matter which calculator you have, we have, let's say, the log of 20 plus the log of 50, and we'll get the valuation of 3. Now, if we have a calculator, that works nice and easy. What this is most likely going to be on, though, is the non-calculator portion, which means I need to know, how do I figure out what this would be without plugging it into a calculator? Well, I'm going to use what we just did. I know that I have a common base right here on my left and on my right. They're both log base 10. And I have an addition sign, which means I can combine these via multiplication. So this is the log of 20 times 50 of my understood base of 10. Now, 20 times 50, 2 times 5 is going to give me a log of 10 with 2 zeros. Let's close our parentheses right here. And the assumed base of 10. Now, what is this expression asking us? This is saying 10 to what power is 1,000? Remember, because I can rewrite this in exponential form, which is drop the base, some unknown. Let's do this in blue so we can see. I'm trying to figure out what the value of this is. So let's use this as an x, some unknown answer. Drop the base, raise to the power of x is equal to 1,000. And with this, okay, 10 raised to what power is 1,000? Well, I need 3 zeros, so that means that x is going to be 3. So what is the power that I'm looking at? That is all valued out to 3. There we go.